Okay, go ahead.
My chair.
This is what chair?
Eyes on.
Pull it the other way. All right, I'll take homework questions first. Anything you want to talk about, and I would suggest, even if you didn't do a lot of it, that you spend a little time going back and making sure you can answer these kinds of questions, particularly when it comes to writing Lewis structures and resonances and using formal charge to evaluate them. So is there anything you want me to show before I go on with the next lesson? That's why I record this class, because I get a lot more stuff onto the video, because you don't ask a lot of questions, so I can just go. That's pretty funny. Right, people in TV land? All right, then I'll just do my presentation, and then we'll be done. And then I'll give you some problems to kind of look at. And then we'll let, let's use the last 10 minutes, and Rishi, you can run the name again. Okay, moving on. I just thought I'd say that enough. I'm going to give you a document that we're going to use to create notes on. This document will be gold. Don't lose it. It will be a chart of VSEPR. Before we go any further, VSEPR is an acronym, but it's actually VSEPR, but everybody says VSEPR, so get over it.
VSEPR or VSEPR?
Right. It's spelled VSEPR, but it's pronounced VSEPR because it sounds pretty. Okay? So today's lesson is about the shapes of molecules in 3 dimensions. Okay? So let me write a few things on the board. This is one theory that explains why molecules take the shapes they take in 3 dimensions. And knowing these shapes is important because the shape of a molecule will affect its properties since it ultimately affects its polarity. This stands for the following terms: valence, shell, electron, pair, repulsion. So the basic idea is that when we think of a central atom to which other atoms or electron pairs are attached, the electron pairs in those bonds or in those lone pairs repel each other. And so they're going to move as far apart as they can in 3-dimensional space. So I'm going to show it to you kind of physically and virtually at the same time. But as I'm doing it, we're going to build this chart. And you're going to have to learn this chart to some extent. But once we get it done, and you've used it for a while, and I show you some kind of like patterns, it won't seem as bad as you think. So I'm going to start on the front where it says AX2. Let me read through what these column headings are and what they mean, and what A and X represent. And then you'll see there's a link here. You can look at this later and play with it on your own. I'm just going to open it up and use it with you so you can kind of see what we're doing. So I love this little simulation because it really makes you able to see what VSEPR is about. And we're going to do the idealized models first. So what you see here are 3 atoms. The stick represents a bond, the ball represents an atom, and the one in the middle is the central atom. Now, I'm going to teach you the basic VSEPR shapes, which all focus on one center. But if you have a complex molecule, you can see these shapes around different centers. So we'll start with simple molecules, and we'll show how we can apply this to even really long and complex molecules. But what I want you to notice is that if I wiggle this molecule around, it keeps going back to the same position. Why? Like, why is it when I shake it and I try to bend it to an angle, it straightens itself up? What do you think's going on? Yeah? Yeah. In other words, this bonding pair and this bonding pair repel each other. So the idea is they're going to get as far apart as they can. And in 3-dimensional space, the farthest apart 2 things can get is 180 degrees away. So no matter how I try to twist this, its best position is where the repulsion is minimized. Okay? Let me kind of show you this with a real model as I do it. Is anybody going to die if I open up these balloons? Who? Who's going to die from a, is anyone really allergic to latex? I have to know this for sure.
Oh wait, latex?
Yeah, I mean, I just want to make sure if like some people are so allergic that if I have it in the room, they start like getting hives. Anybody like that? I didn't see it on the list, I just want to make sure I didn't miss it. So I have to make identical balloons to kind of show what this is showing. I need a little bit of slack. That's going to be my atom. Perfect. So I'm going to take this balloon and this balloon and try to model what I'm talking about. I'm going to make them about the same size. A little bit. Perfect. So here's what I'm going to do. I'm going to kind of build these shapes as I go by just tying balloons together. So if I take the two ends of these balloons and wrap them together, you'll notice that, one of them's smaller, dang. You'll notice that naturally they tend, because of their pressing against each other, they tend to kind of go opposite each other. They push apart in a line. In the same way that those electron pairs repel and push themselves in a line. So we have names for that phenomenon. We have a name for the shape. But we have to be really careful here. I'm going to click on here and talk about the electron geometry versus the molecular geometry. Okay? So to make sense of this, you'll notice that the first box that we're solving says AX2. What does that mean? In VSEPR language, A represents the central atom to which everything else is attached. X represents attached atoms to the central atom. And finally, if there's lone pairs on the central atom, we designate them with an E. So if I had a lone pair, like for example, if I slapped a lone pair on here, that would be considered E. So this would be any lone pairs, but only the ones on the middle atom, because they influence the shape. In fact, did you see what happened when I added the lone pair? What happened to the molecular shape? Yeah, in other words, what we're saying is the lone pairs or the bonding pairs all repel each other. So they're going to spread out as much as they can in the space that they have. So I went from a molecule that was originally straight because two bonding pairs can push away from each other 180 degrees. So they lined up like this. And when I added a lone pair, that repulsion bent these away from the lone pair. And so we changed the shape just by doing that. Okay? That's the essence of what this is about. Now we just have to look for the patterns and the names. So the first molecule on the chart that I've given you is the example beryllium chloride. Okay? Now, look at the next term you need to know. What we call an electron domain. Domain here just means region. Okay? What can count as an electron domain is the following. It could be a bond, and whether it's single, double, or triple doesn't matter. We treat them as one domain. A domain is just a region of electron density. So if there's a bond here, this counts as a domain. Lone pairs can count as domains too. They influence the shape of the molecule because, again, as a region of high electron density, there's negative charge there that repels the other negative charge. Yeah, so basically, when I'm looking at this molecule, the code is AX2. That means it has two domains, 1, 2, and both domains are bonding. In that case, if you look at that first box after AX2, it says electron domains around the central atom. Please put the number 2 there. So in the first box, where it asks for domains, put 2. How many of those domains are bonding? How many of the domains are involved in bonds in this case? Well, look at the image. Aren't both of them involved in a bond? So where it says bonding or shared pairs, please put 2. Right next door. Where it says non-bonding or lone pairs, in this case, it's 0. There are no lone pairs on this central atom. Now, here's where we have to distinguish between the domain geometry, meaning what are the electron pairs doing, versus the molecular geometry. Let me define the difference. When I'm looking at the domain geometry, I'm looking at the arrangement of all the electron pairs in space. So the geometry or shape for this, you include all the electron pairs. Electron geometry include the bonding and the lone pairs. Okay? So what's interesting is the electron domain geometries, there's only 5 of them you have to know. And they're the basis of everything else. Once you know those 5, all the other ones are derivatives of those. In this case then, when it asks for the electron domain geometry, we can see right here that the 2 domains are 180 degrees apart. The name for that type of shape in chemistry, oddly enough, is linear. So in the box where it says electron domain geometry, kindly write the word linear. So I know I don't have the table up here, but you see I'm just following along the row. You should be able to follow along with it. Now in this case, the molecular geometry, that's looking at something else. That's looking at the arrangement of the atoms themselves in space. So this geometry is based on the arrangement of atoms, not just the electron pairs. So in this case, again, just the simplest one, if you look at all 3 atoms, they are in a line. So the molecular geometry, which focuses on how the atoms are arranged, is also linear. Now, where it says example, I gave you a molecule that obeys this shape. And for that, I'm asking you to write the Lewis structure. So for beryllium chloride, you would find something that looked like this Lewis structure. Notice it fits the description. There's an A, there's 2 X's, and there's no lone pairs on this middle atom. So this molecule fits the shape AX2, which we have just shown is linear. So here's my dot structure. And then when it says sketch it with bond angles, I'm going to draw a model that looks something like this. So to sketch it, I would just write a circle in the middle, an attachment to each side, and for the bond angle, we get 180 degrees. Any questions? Okay, so I'm just going to continue this now. You've seen how I'm defining things. I'm just going to go through the whole chart with you and just build models as I show them to you. If you have any questions, just ask. But our goal is to get all the different shapes that tie to the specific types of Lewis structures that we can draw. Are we doing okay so far? Okay. So I'm going to clean the board and just kind of work through row by row. Now, that is the simplest molecule you can basically have in this context. 3 atoms in a line. The 3 atoms don't always make a line. Let's look at a 3rd atom. If I attach a 3rd atom here and make it an AX3, which is the very next group, what shape do you think we're going to get? Good. Not only is it a triangle, but it's an equilateral triangle and it's flat. It's 2-dimensional. This is the best we can get spread out in this arrangement. If I try to move an atom into a, like farther from one, it gets closer to the other, and no matter how I wiggle it, it will still come back to its most natural and stable shape. In this case, you will see that we have, in this example, the following designation. 1 center and 3 attachments. AX3. You will notice that it has 3 domains, meaning 3 regions of electron density. You will notice that they're all bonding domains. So where it says total domains is 3, bonding domains is 3, the non-bonding is 0. None of them are lone pairs yet. Now we can illustrate the shapes. The domains point along the corners of an equilateral triangle. But that's not, we can't just say that, we have to use the fancy chemistry term. This is called trigonal planar. Planar just means flat. They're all in the same plane. So trigonal means triangular, planar means flat. This shape, both the domains and the atoms, both of them line up as trigonal planar. That's what this is called. Let's see if the balloons agree. I'll try to blow the balloon a little more better this time. I like used to make balloon animals here. Okay, here we go. Oh my gosh, look at that! It's trigonal planar. Look at that, isn't that beautiful? It did it all by itself. I didn't even have to make it do that. It's staying that way because this way the pushes of the balloons balance out the rest. I see you are not easily amused. All right, moving on. Now, if we start evolving this particular shape, what I'm going to now do is show examples where I can pluck atoms off and replace them with lone pairs. But first, let's finish this one. The example I gave here was BF3. So the Lewis structure is going to look like this, which we said is okay. It's another one of our exceptions to the octet. Notice how this Lewis structure translates to AX3, but no lone pairs on the middle atom. So this shows itself as AX3, which is why it fits this shape profile of trigonal planar. Okay? And then if you want to sketch this with the bond angles, all I'm asking you to sketch is something that looks like that picture. Try to make it as realistic as you can, and then just illustrate one of the bond angles. Which that should make sense. If it's an equilateral triangle, it should slice the 360 into 1/3. Okay so far? So what I'm getting at is once you have this chart, if you build a molecule or do its Lewis structure and it comes out AX3, this is the shape we expect it to have. All right, in this case, or moving on to the next case, watch what happens when I take one atom off and replace it with a lone pair. Here, for the first time, our domain geometry and our molecule geometry are not the same. You see, the domains are still pointing to the 3 corners of the triangle. So the way the electrons are arranging is still in a flat triangle. But if we focus on the atoms and what that would look like in space, we just see a bent angle, right? We just see this angle. So this molecule is called bent. Notice, 3 domains is still trigonal planar. But the molecule itself, where the atoms look like in space, is bent. So I can show you that with these models as well. I've got these little model kits that are kind of cool to play with. So what I'm talking about would look something like this. Oops, wrong one. Here is AX3. Notice the gray sticks are the domains. The atoms are the white balls connected to the central ball in the middle. That's another atom. Equilateral triangle, trigonal planar. The sticks and the atoms. But what I did is I took one of the connections off and replaced it with this fun little lone pair. So when you see this, what you're seeing is 3 sets of electrons. 2 are bonding, 1 is non-bonding. One is a lone pair. But they still arrange as far apart as they can into the flat triangle. But if you focus on the atoms, which is what you'd physically see in the real world, right? You don't see the electron going. you would see what looks like an angular molecule. And that's why it's called back. Am I clear on this? Like the difference between the electrons and the molecule shape? Or are we confused on that? It's okay? Luca, are you good? As long as Luca's got it, I'm going on. Okay. Now, that kind of concludes the first two families of these molecules. The AX2 is the head of its family, but it's the only member. The AX3 has two members. When I say family, what am I talking about? What makes them related? What makes them cousins? What do the second and third molecule that I gave here have in common? What's the same for both? The domain number, right? So everybody with 3 domains is in the same family. Everybody with 4 domains is in the same family. Let's look at the 4-domain family next. So if there's 4 domains, this is the first time we're going to pop into 3 dimensions. Let me show you what I mean. Oh, we didn't do this one's Lewis structure, sorry. Let's finish this one first. I'm rushing ahead of myself. So the example for this one was NO2 minus. By the way, am I going too fast for you to kind of fill in the table? Or keeping up? All right, NO2 minus. What's the Lewis structure here? 5, 6, and 12 is 18 valence electrons. So it's going to look something like this. Oh no, I ran out of electrons, whatever will I do? How do I fix nitrogen if I'm out of electrons? What? Speak up! All right, Rishi, you know, say it. So you just sat there. You just sat there in silence while I'm sweating up here by myself. I'm dying up here in front of the audience. Thanks, Rishi. Not your fault. I'm looking for someone else to blame. Sorry, I'll blame you now. Okay. So we have to make a double bond. But wait, Rishi. How do I know to make the double bond on this side? He said the word. Woo, woo, woo. I'd have to draw it both ways. The bond order here would be 1.5. But to save space, I'm just going to write the word res underneath, because this is one of those equivalent resonance structures I have to show. But that doesn't affect the VSEPR shape. This is still A, X2, here's your E1. This lone pair is the E. So this molecule is an AX2E1, which is why it has 3 domains. And if there's 3 domains, we automatically know that the shape of that is trigonal planar. But the molecule only has these atoms, and the molecule is bent. That's the kind of thing you have to see here from the Lewis structure, which is why writing the Lewis structure is correctly so important. All right, I'm just going to keep going happily along until somebody interrupts me with a question. Moving on. Man, I'm going to look so stupid on that video later. All right, let's go now to the next family, AX4. Dun, dun, dun. Eliminate lone pair, add 2 atoms. What the heck is this? It's in 3D. I wonder if the balloons do that. This gets harder as I go on to get them to fit without knocking them all apart. Oh man! Ah! I'm trying to do this without making it a permanent. All right. Not to mention my deathly fear of balloons that I'm sure I've told you about earlier. I think I took my medicine. Now, I'm not trying to force this into a particular shape. I'm just, hold that. Hold this until I need it. I'm tying them together this time. I'm no fool. Fool? No. Show you guys. I'm talking the balloons, by the way. Thank you. Oh, couldn't hold it yourself, eh? Now I'm going to make you hold it. Oh, wait, does it make you nervous? Here, you hold this. I don't want to make you nervous. Can I have my balloon, please? Jesus. Think it's easy. Aha! Oh, it was worth it! Ah. Does anybody know what this shape is? You learned it in math. It's a regular four-sided figure, a four-sided pyramid that's all equilateral.
Equilateral pyramid?
No, but that's a good guess. It rhymes with schmetrahedron.
Hexahedron?
Tetrahedron. This is a tetrahedron. It's a four-sided pyramid where all the faces are basically triangles. But you might have thought, oh wait, if there's four things around the middle, why doesn't it make like a plus sign? Well, if it made a plus sign, what would the angles between the atoms or domains be? What would this angle be in a plus sign? 90. But if you look at a tetrahedron, the angles are all 109.5. So what does that tell you? Well, they're farther apart when they do this. So because we live in a three-dimensional world, this is the shape that four domains will adopt. So now when we look, this is our AX4 model. AX4, A, X, 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 no lone pairs. Both the domains, meaning the electrons, and the atoms create a a four-sided tetrahedron. So we call the shape tetrahedral. In this case, we used the common example of methane, which is an easy one to do the Lewis structure of. But methane, when we draw the Lewis structure in 2 dimensions, looks like a plus sign. And this is the place where everybody makes this mistake at least once. At some point in the homework, I'm going to ask you to figure out what is the bond angle in this molecule. And you're going to look at it, and your brain is going to say what? Your brain is going to say 90. But your chemistry brain is going to go, wait a minute. This is a 4-domain molecule in 3 dimensions. It's going to have an angle that's bigger than 90 because this forms a tetrahedral shape. And those angles are 109.5 degrees. You got to know that angle, actually. So this is one of the key ones. This is a big one because carbon does this a lot in organic chemistry. It forms this type of kind of saturation of 4 bonds. And it makes this tetrahedrons within the molecular structure. Are we still cool? So I'm going to finish this family by successively replacing each atom with a lone pair and showing examples of those types of shapes. Again, what's not going to change in this family is the number of domains. Whether I'm doing AX4, AX3E1, or AX2E2, all of these have 4 domains. So all of the domain shapes will keep being tetrahedral. But the molecular shapes, how the atoms are arranged, are going to keep changing. So watch what happens if I replace one atom with one lone pair. I now have what looks like a triangular pyramid with one of the corners being the lone pair. This is the AX3E1 model. The domains are still 109 apart, 109.5, so it's still tetrahedral there. But the shape of the molecule is called trigonal pyramidal. So when you hear planar, it's flat. When you hear pyramidal, that means it's going to be bent into the shape of a pyramid. So that molecule is considered trigonal pyramidal. I can show it on this model better than with the balloons, actually. So let me do that. here was the methane in the form of the original AX4 structure that matches our balloons. This is methane. What I just did is pluck this off and replaced it with a lone pair. That lone pair is what pushes these atoms down and bends the structure so it doesn't stay flat or planar. This is a model of the molecule ammonia. What does that look like? Well, we replaced this with N, we replaced this with lone pair, and now we have AX3E1. AX3E1. These bond angles are still considered 109.5, but here's an important point. The lone pair spreads out in space more, so it has a squashing effect. So make a note. When you go to this situation with the lone pairs, it starts compressing the angle. So it's actually going to be less than 109.5 in this case. Just enough to know that. Turns out in this molecule it's about 107 degrees. You don't have to know that specifically. Just know that lone pairs tend to spread out and squash the ideal angles a little bit. Okay? Again, I don't know if you filled out this chart, but even if you fill out the chart later, all these questions about how many domains, you should be able to figure that out just from the Lewis structures. So even if you don't get it all done in class, you should be able to still get it done on your own. But here, again, we have the AX3E1 trigonal pyramidal for the shape of the molecule, but the domains are still arranged in the tetrahedron. If I just say geometry, assume I mean molecular. One more time, knock off an atom, replace it with a lone pair, and now you can see we're back to having a bent molecule. So now we're doing this one, and the classic example is water. AX2E2 is the classic example of water, because look at what water is. The Lewis structure has two attachments of hydrogen to oxygen and two lone pairs. AX2E2. And what it does is it creates another type of bent molecule. I'd like to take a moment to refer to the water molecule being bent, because it's why we exist at all. So what we're going to learn in the very next lesson after today is that the bending of the water molecule leads to its polarity. Okay? This little water molecule is bent because of lone pairs. Now watch what happens. Water bent has a boiling point of 100 degrees Celsius. If we were just to do this, take a water molecule shape and do that and make it a line, water's boiling point would be negative 80 degrees Celsius. Why would that matter to life on Earth? What would water exist like on Earth if its boiling point was that low? Gas. It would all be gas. Liquid oceans would not exist on Earth, and therefore, since life evolved in them, neither would we. This much difference in the universe, from here to here, makes the difference whether life as we know it can exist. Crazy. Here to here. That one little change is the difference between life evolving on Earth and not, or one of them. So, again, the shapes of the molecules matter. All right, we've done the first side. Flip it over, and let's finish the back, because up to now, we've done everything up through the octet rule. The back side is going to require us to use hypervalence, meaning expanded octets. So in our very next example, we're going to cover the 5-domain family, AX5 and its affiliates. Let's start with AX5. This shape's a little harder to visualize. But here it is. So I'm going to turn it so you can kind of see what I'm looking at. You see there's a flat triangle in the middle? And then if I flip it over, there's a line that goes through the triangle. It's kind of a weird shape. Let's see if the balloons have anything to say about it. It's going to start getting tight. All right, I think I can do this. It's a steady hand. Yeah, I'm gonna fail. Unless I twist it just the right way. Aha! Maybe. Oh, I got an idea. I know too. Is this at least mildly entertaining to watch me just bumble around up here? Good. Get something out of it. And there's no commercials. As far as I know. All right, I'll tie these two together, those three together, then I'll twist the two sets together, and voila! Oh. How did you come out? Tough, eh? Fix you. Can you tell I've done this before? I will twist you around that one and under. Aha! Now we're getting. Okay. That stupid balloon was too small. All right, it's deformed, but I got it. You see it? You see the triangle in the middle? You see the two on the ends? Guess what we call that shape? Trigonal bipyramidal. It's like two triangle pyramids connected at one base. So they had to call it something goofy.
Trigonal bipyramidal.
What does that look like? I'm glad you asked.
It looks like this.
Ring, 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 ring. Here's a pyramid. Here's a pyramid. It's a bipyramid. There's two pyramids. They have a common triangular base. The angles inside are just the triangle angle of 120. The angles here are 90s, and across this area is 180. The positions top and bottom are called axial positions, and around the triangle are called equatorial. I don't care if you know those terms, but I'm just pointing it out. It makes a difference when I start changing this to have lone pairs, where I put them. The more stable place is in the equatorial position. So what you're going to see me now do is evolve this shape 3 times by replacing one of the triangle atoms with a lone pair over and over again. Okay? So we're going to go through this kind of in the rapid fire way. Right now, we see the shape. The molecule here, I believe, was phosphorus pentachloride. So we were doing the chart. It would look like this. Again, we don't look at the Lewis structure as giving us accurate shape information. It's VSEPR that kind of tells us how it looks in 3D. So this is how you might draw the phosphorus pentachloride Lewis structure. A, X5, and it's trigonal bipyramidal. Now, replace an atom. Oh, by the way, when you're sketching these things, I'm not really good at it. There's some people who are really good at the 3D perspective. It's good enough for me if you do something like this. Just try to kind of get the triangle in place and the line through it. And you know what helps to see the triangle? If you do like a dotted line here, 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 then you can kind of see that's like a plane, and this is going through it. Whatever, you guys are better artists than I am. Okay? I've been a decent dresser, but I'm not a very good drawer. Get it? Dresser, drawer? Ha! That's a knee slapper. What would you do if I just walked in one day and stood here and said nothing for 40? Would you even react? Or would we all just stare at each other like this for 4 minutes? We're gonna try that. Maybe next week. All right. Anyway. Woohoo! Let's replace an atom.
Atom off, lone pair on. What the heck does that look like to you? Think of your favorite childhood park toy.
What is it? Oh. Yes!
When I take off one of the atoms from the trigonal bipyramid, I take it from the triangle and replace it with a lone pair. And now we have a little seesaw.
See, chemists have a sense of humor. Yes, the shape is called seesaw. A, X4, E1. A is the middle. 4 attachments, 1 lone pair.
This has the classical analog of the molecule sulfur tetrafluoride.
Sulfur, 4 fluorines,
And a lone pair A, X4, E1 coding 5 domains. The domains follow a trigonal bipyramidal arrangement, but the molecule is called seesaw because it makes a seesaw.
see? Saw. See? Saw. Seesaw, seesaw, seesaw. Yes, I am starting to freak out. Okay, moving on. What if I clip another atom and slap another lone pair? BAM! What does that look like to you? It's called T-shaped. How clever! But look, it still has 5 domains.
1, 2, 3, 4, 5. They still arrange in a trigonal bipyramidal arrangement.
But the molecule just looks at the atom. And so the shape of the molecule is T-shaped. Isn't that impressive?
Now, the molecule I used example is BRF3, bromine trifluoride. Watch what I'm going to do here. It's so simple. I take this one, and I take it, I make it a bromine. I take one of these off, I put another lone pair. Look at that. A, X3, E2.
And I make a molecule that looks like a T.
When you're sketching the geometric figures, you do not typically put the lone pairs on it, okay? The lone pairs go in the Lewis structure, but not in the model.
Well, my friends, we are coming close to the end of this discussion. Let me replace one of the lone pairs. And now you have the T.
Fascinating.
One more in this family. We'll knock off yet one more atom and replace with lone pair. Oh my gosh, is it possible? What is going on here? What have we made?
Well, there are still 5 domains. The domains are still trigonal bipyramidal.
But there's only 2 atoms left, and the way the lone pairs balance out, the atoms line up. It's a linear molecule. Look. Wah, 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 wah. They line up again. Look at that. Well, I'll be.
And it looks like a power.
One more family, and I'm finished with you for today. Only 3 examples to go. Hang in there, you'll net it, and then I'll shut up, give you some problems to pretend you're doing, and then we'll all pretend we're working while we just sit around. Oh crap, that's on video. That was a joke. Okay. Oh crap, I said crap. I did it again! Twice. Alright, let's go to the last model. We'll take care of that in post-production. And now your favorite one of all.
AX6.
What does that look like to you from your childhood? Nothing. We played on the internet. Yes! Remember jacks? They look like that. And you bounce the ball and you try to pick them up. And you bounce the ball twice and you pick up more. It's a stupid game. Let's build one.
Where's my atom that is for this? Did somebody take my last atom? Oh no.
Uno, dos, tres, catorce, cinco, sienta. There, 6.
That has a name.
Now there's 6, but it's called octahedral. Why is it called octahedral if there's 6 atoms? What is a hedron in math? It's not a vertex, it's a side. Look at this figure. Imagine connecting the dots and you would get 4 sides on top and 4 sides on the bottom for a regular polygon known as an octahedron. So this is considered octahedral geometry. Again, the domains and the atoms are the same in this first example because there's an attachment at each domain. But what I'm going to do is pluck atoms off and replace lone pairs and see how the shape changes. So the first one I'm going to pluck doesn't matter, they're all equivalent. So let's pluck one off. And replace it with a lone pair. What you have now is a pyramid with a square base, which we cleverly call
Square pyramidal.
because it's a pyramid with a square base. Right. Now, in our octahedron, all our angles are 90. That should have been pretty obvious. But now, where I kind of flex to the last example that we need, it makes a difference where I pluck from. Because if I pluck from 90 degrees, those lone pairs are closer and more repulsive. So they're going to go to opposite end. So the last one you have to see and know is AX4E2. Square planar. And I'll fill in the examples in just a minute. I just wanted to kind of get to the end of the thing there. But you see, they end up as a flat square. Square planar. It's just that simple. To fill in the Lewis structures for the last couple, we had SF6. And I kind of like showing them evolve. So SF6 would have looked like that. Are you guys okay if I don't put all the lone pairs on fluorine for now? Will you forgive me ever? Okay. Octahedral. So if you were drawing it, you might do something like this. And again, to help you see the shape of the plane, you might just connect the dots there just so you can see the square in the middle. The angles are 90 degrees everywhere here. Tetrahedral. Knock off one of these and put a lone pair. Now you've got square planar. Square pyramidal. Knock off another one and put a lone pair there. Now you've got square planar. So what's the key to this game? Memorize right away the fundamental heads of each family, meaning the ones that are at the top of each starting list. AX2, AX3, AX4, AX5, AX6. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Once you know these solidly, all the others are derivatives. They're all just taking these and changing them by replacing an atom with a lone pair and then changing the name of the shape of the molecule. That's it. Thank you. Let us build one more balloon into this so I can get a little more frustrated. And then I'm going to just give you the problems to kind of look at and work on, okay? See if you can actually learn this stuff. Perfect. See, can he get the octahedron? Can he build it? The looks on your faces, the sheer terror and excitement. I wish the camera could see it right now. It's unbelievable. We're getting there. Something's happening. Oh my. Okay, it's not. I gotta get a better way to do this. have you. What if I twist these? I never did the balloon animal thing. That's probably why I can't. Twist this one around that one. Huh? And this. I'm back to where I started. If I'm kidding. What the? It's kind of sad, isn't it? I'm really kind of getting depressed over this. It's pathetic. But it gives you all something to laugh at. If I twist this one here very carefully, place it into this position. Oh! Look at me now, world! I have an octahedron, and I'm not afraid to use it. Pass it around. Why not? I worked so hard on it! Now, seriously. Oh, by the way, watch this. With the chart in front of you, AX2, linear. AX3, trigonal planar. AX2E1, boom. AX4, tetrahedral. AX3E1, trigonal pyramidal. AX2E2, bend. Oh, we didn't put the angle on the bend here, did we? Oh, we already knew it was 109. AX5, trigonal bipyramidal. AX4E1, seesaw. AX3E2, T. AX2E3, linear. The black ones are lone pairs. AX6, octahedral. AX5E1, square pyramidal. AX4E2, square planar. It's all right here. Here's your chart. Thank you! I got some applause! Look at that! Did you hear that applause? That's louder than like a golf clap. Thank you, thank you. Okay, so here are the problems I want you to look at. I have some practice sheets, but let's just go right into the problem set, which I didn't put on here. So we'll do the practice.
My bad.
Let me just do this real quick. Just try. Where's my best?
Oh.
I know.
Would you like to add first? Oh. Wait, do you want to see what? I just want you to see this one.
That's not the right one yet.
This one filter that I've come across, and it's ever changed my life. Let me see.
Hold on.
Wait. No, I'm
Ooh, I know. I'm a genius. I'm a genius. You have the worksheet from the other day?
No.
Probably not. Does anybody need it?
Anyway.
Okay. So instead of starting something new, here's what I want you to do right now.
Wait. I'm not done.
Let's try to figure out some of the shapes of the molecules on here. Okay? So let's try to do as many as we can.
You get it?
I'll do the first one with you. Look at NO plus. Do I have to do anything to work out the shape if there's only two atoms? What's the shape of a molecule if there's only two atoms? Thank you. So let's move on. Let's do carbonate, CO3 minus 2 together. So you already have the Lewis structure, don't you? If you solve these? So if you do, you have a resonance structure of carbon dioxide that looks like this. VSEPR, you can apply any resonance structure you like. It doesn't matter. So, first thing I want you to do is label it with AXE. How would you designate that structure, AXE? A, X3, are there any lone pairs on the middle? No. So this is just AX3. If that's true, what shape should this molecule have? It's trigonal planar. That's it. That's what I'm asking you to figure out right now. Go through those Lewis structures, label them with the AXE stuff, and then see if you can figure out their shape. And then just record the shape. Just give me the AXE and what the shape is called. If you really want to be fancy, sketch it and you'll start learning what they look like. But I'm not going to collect this. This is just for you to work on now. Right? Work on it now. I'm not giving you any homework over the break. Thank you. I'm done for today. You guys can try to figure this stuff out or
Yeah.
try to have Rishi do the name game. Your turn.
It's okay.
It's Balloony! Oh. Well, you got the eyelashes right. At least I'm smiling. Let's see if anyone recognizes that it's not me. Ah, I tried to break it and I failed.